Okay, so let's go ahead and do the second part here. This part is actually quite important, okay? So we're going to do connecting differential and integral calculus. This kind of sets us up for the fundamental theorem of calculus, okay? So this is kind of a preview to that, all right? So let's go ahead and go to page 297. On page 297, there's an exploration 2. So let's go ahead and do that together, okay? So this is the group activity. Suppose we are given a graph of a continuous function f as in figure 6.30. Number 1, copy the graph of f onto your own paper. Choose x greater than a in the interval a to b and mark it on the x-axis. So everybody do this together. Okay, so you guys do this on your own paper, and we're gonna have like this. Okay, and I'm gonna go ahead and go from A to B here. Okay, so we're gonna go ahead and mark an X. I'm gonna go ahead and mark my X like this. Okay, and mark it on the x-axis. 2, using only vertical line segments, shade in the region between the graph of f and the x-axis from A to X. A to X. So we're going to shade it in vertical lines like this. And we're going to shade it until I get to X. Okay, you guys do the same thing. Okay. 3, your shaded region represents the accumulator function. So this guy here is the accumulator function. So it's from A to X, f of t dt. This is f of x, okay? The reason why I cannot use x here is because I can't have that in here and up here at the same time. Okay, so I'm using the dummy variable t here to represent the area under this curve here. Okay, so it's the accumulator function because, again, as x goes forward, you accumulate more, and it's the accumulator function that we talked about before, right? So your shaded region represents that, and we're going to call this large f of x, the accumulator function, large f of x, because this is a function of x. As x moves along, this guy changes, right? So that's a function of x. So it's large f of x. Okay, and we're going to call the accumulator function, we'll call that large f of x. Number 4, recall that f prime x is the limit of, so f prime of x is the limit as delta x goes to 0, it is delta f of x over delta x. Okay? So as x gets smaller and smaller, so represent delta f in your picture by drawing one more vertical shading segment to the right of the last one you drew. So we're going to put one more here, right here, okay? And we're going to call that f, so that's what we're going to call it, so we're going to do that, right? We're going to drawing one more, draw that too. Delta f is the sine area of your vertical segment. So it's this guy right here, this red line here, okay? 5, represent delta x in your picture by moving x beneath your, so it's going to be, delta x is going to be from here to here, right? We're going to call that delta x. It's that little region right here from x to the next x, so it's delta x, okay? So as delta x goes to 0, what happens? Can you see that this is going to be the same as your f of x at that point, right? At x, because delta x is going to go to 0, so I'm going to move it going that way, so it becomes f of x, okay? So what is now the height of your vertical segment? 7. Can you see by Newton and Leibniz why Newton and Leibniz concluded that f prime, that large f prime of x, is the same as the small f of x. Can you see that? Everybody see that? Right? So the delta, so the f prime of the large accumulator function basically becomes f of x. Okay, and that is in the middle of 297 in the green box there. So since f of x is this guy right here, what we're saying is that the derivative of this guy, the derivative of this guy is the same as the derivative of this guy, which is essentially f of x. Okay? So the derivative of the accumulator function basically becomes f of x. Okay? So if we're going to do a definite integral, if I'm going to go from a, so we're going to go where? So this means that the integral is an antiderivative of f. In fact, we can exploit the following range because we can go and write that can you see that this is, since this is the accumulator function, right? If I take this is the same as plus c. If I take the derivative now of this guy, and I take the derivative of this guy, I'm going to get here d dx, a dx, f t dt is equal to f prime of c, and the c goes away because it's a constant, right? Okay, which is the same as f of x. Okay, so if you do that, you can actually find now, we can find, let's go back here. Let's go back from here. We're going to go ahead and do a little trick, and we're going to find out what c is. Okay, and the trick we're going to use here is we're going to call x, we're going to use x is equal to a. If x equals to a, then this guy becomes a, correct? This guy becomes a. But now I have a situation where we're going from a to a. So this guy actually becomes 0. Can you see that? So the c here is going to be equal to negative f of a. So let's go back to where we were. We were here, and this was x, right? This is where we were, but we solved for c. We now know that c is negative f of a. Okay? So, what you really found, now let's go ahead and rewrite this. Let's go ahead and rewrite this. We found that a to b f of x dx that. So if I know what the antiderivative of this function is, okay, if I know what the antiderivative of this function, I can go ahead and now find out what this is. Okay, so given that, now let's go back. Let's go back to page, where was it? Page 295. Let's go back to 295. There was an example there that we didn't know how to do, and so we had to use the FNINT, and that was, we were trying to go from 0 to 3, 4 minus x squared d of x. We didn't know how to do that, and we had to use our FNINT. So now, let's see if we can actually use this and actually solve this algebraically. Okay, so what would be the antiderivative of this? What would be the function that when I take the derivative, I'm going to get this. That's what we're looking for, right? So what's 4? What would 4 be? What would the antiderivative of 4 be?
4x.
4x. Great. What about negative x squared? What do I, when I take the derivative, do I get x squared?
1/3 x cubed.
1/3 x cubed. And I'm going to evaluate this from 0 to 3. So I'm going to find f of 3. So I'm going to put 3 in here, right? So it'll be 4 times 3 minus 1/3 3 cubed. Now I'm going to put the 0 over here. So I'm going to put 0 in here. What do I get when I put 0 in here? I get 0 minus 0. Right? So this is the same as 12 minus, this is 27. 1/3 of 27 is 9. Voila. Ding, 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 ding. This is where your 3 came from. Okay? All right? So now we actually know how to do that. Okay? Let's go to back to page 298. On page 298, there's an example number 4. Let's see if we can do that. Example number 4 says find 0 to pi sine x dx. Okay, so we're going to do what? We need to find the antiderivative of sine x. What's the antiderivative of sine x?
Cosine?
Close, almost, but not quite.
Minus negative cosine.
Negative cosine x, right? Because when you take the cosine, x becomes the negative, right? The negative, right? Okay. 0 to pi. So again, I'm going to go negative cosine pi minus negative cosine 0. Cosine pi is what? What's cosine pi? Let's go back.
-1.
-1, right? So this would be pi, right? So it's going to be -1. So it's going to be -1 minus, what's cosine 0?
1.
Right? Remember we talked about this. We did the exploration. We did the exploration and we said, oh, if you're here, and we said this was going to be 2, remember, right? We did the exploration on that. Indeed, it is 2. From 0 to pi, sine of x, the area underneath that curve is 2. Okay, so that kind of goes back and ties that together from when we did the exploration. Okay, all right, we're done for the day.